In this video, we are going to discuss application of state machines in hardware. Now, those of you who are interested in microcontroller projects like using Arduino or Raspberry Pi can take their skills to the next level by learning finite state automata. Now, it is used everywhere, whether you are talking about the control of a microwave or a washing machine. In so many different places, state machines are used. Now, in our talk, we shall take a rather simple application, that of a coin dropper. So, we are all familiar with such coin droppers where there is a slot and we insert a coin. Now, in our example, we shall work with two different coins of different sizes, and we want to sense which type of coin has been dropped based on just the size. Now, most of us are kind of familiar with how such things are done. They are done using two sensors. So, there are two light emitting diodes placed in the path of the coins. One placed in such a way such that both the coins will hit this, and the other one will be hit only by the larger coin. So let's see how it works. Suppose I drop a 10 rupees coin. So initially both the lamps are on and the sensor can see both of them. So there are sensors facing them. So the 10 rupees coin comes up, and right at this point the lower light cannot be seen anymore because it has been obstructed by the 10 rupee coin, but this is still on. Now, as the coin continues to roll, it will cover both the things, and then as it moves past, it will again reveal the top light, but this is still hidden, and then it will roll completely out. At that point, the sensor should report that the amount is rupees 10. Similarly, if now a fiver comes up, it will cover only the lower lamp, and then it will roll away, and then the amount will be increased to 15. And you can keep on adding more and more coins, and every time a coin rolls by, its amount will be added. Now, this is done using a finite state machine. But first, let's understand what the sensors tell us. So, there is the red sensor and there is a blue sensor. Initially, both the sensors are on because the light can be seen. So, I will draw it here as a graph. This is for the red, it is on and it is off, and here for the blue one also it is on. Now, when the tenor comes, the blue one is shut off, so the blue one now goes down, but the red one, it still continues to move. Then, as both the things get covered up, even this top lamp also goes off, and the bottom lamp is anyway off. I mean, the lamp is on, but the sensor cannot see it. Now, as it moves further, the red lamp comes on. So, the red lamp will now come on. The blue one continues to remain off. And when it completely moves out, then the blue one will also become up. So, this is how the graph will look like for the tenor. Now, in case of the 5 coin, the blue one will go down, and then you can see it will come up. Oh, sorry, I am still working with the, well, I will just let the tenor coin move. So, I will of course assume that you cannot really make both the coins enter the slot in the same time. So, let's work with the fiver. Now, the fiver has moved out, so now the blue thing will come up. But here, the red one was all along high. So, this particular structure is for the red coin and this is for the blue coin. Now, here I can see the graph and hence I can conclude, but in practice, the sensor only sees the values at any single time instant. So, it has to remember something from the past in order to locate itself along the timeline. So, let's see how we can use a state machine to do that. Now this is a typical state machine in a hardware setup. So you can see this ball is just continues to move because we are always sensing the two sensors. That is why this is always active. Even if there is no coin, you are always sensing that there is no coin. So at state 0, it is no. This NN stands for on, F stands for off. So when I say NF, this means the upper one is on and the lower one is off. So let's see what happens when the tenor comes in. So immediately it got the input NF, the upper one is on, the lower one is off, and now it is stuck there because this continuous sampling of the two sensors is going on at a very rapid pace of the order of milliseconds. So there will be lots of times that this thing will go round and round before the coin can move past. Now it moves further. Now it gets the input FF, meaning both of them are off, and it has come here, and then it moves further and it has now come to state 3, means it has gone past, and then it will get NN and will be back in the original state. Now here you have some output. So the green arrow says add 10 to the amount. So whatever was the original amount, in this case it was 0, I added 10 and displayed it. And now let us see what happens if I use the 5 coin. Then it comes to this state and immediately it will go back to this state and pass to the blue arrow which says add 5 to the amount, and it will get 15. So you see, this simple state machine keeps track of which coin is being rolled. And you can make it more sophisticated. For example, you can try to make it tamper-proof. Someone might try to just insert something other than a coin in order to prevent light from reaching the sensor. If accidentally you just block this one, you just block only the top light. In that case, that is an impossibility because no coin can possibly block the top light, keeping the bottom light revealed. So that is a tamper case. You can also just deal with the same thing using this very state diagram, possibly adding one extra state. So you can try to think about that. So you can make it as complicated as you like and still remain within the formalization of a state machine.